Good afternoon. Welcome back. Thank you for joining us. I'm Steve.
And I'm Scott.
And together we're Backyard Musings, broadcasting live Apple Valley, People's Republic of California.
Yep, and we're talking a pretty crazy story this afternoon.
We did a story a while back about neutrino generators because they're all around. Doesn't matter day or night, and just something to collect and have energy. This is really interesting.
This is weird.
Supercooling radioactive atoms could create a laser-like neutrino beam, potentially opening a new avenue for studying these elusive particles and even enabling novel forms of communication. So a burst of this could have communication in it, and the receiver decodes it. Every instant, torrents of neutrinos pass through our bodies and the objects around us without leaving a trace. Smaller than electrons and lighter than protons, these ghost-like particles are the most abundant massive particles in the universe. Would you like to know more?
The exact mass of a neutrino remains unknown because they are minute and interact only rarely with matter. Measuring them is extraordinarily challenging. To probe this, scientists use nuclear reactors and large particle accelerators to create unstable atoms that decay into several byproducts, including neutrinos. These facilities produce beams of neutrinos that researchers can study for properties such as mass.
MIT physicists now describe a much more compact and efficient approach to producing neutrinos that could be carried out on a tabletop. In a paper appearing in Physical Review Letters, the physicists introduced the concept for a neutrino laser, a burst of neutrinos that could be produced by laser cooling a gas of radioactive atoms down to temperatures colder than interstellar space. At such frigid temps, the team predicts the atoms should behave as one quantum entity and radioactively decay in sync.
The decay of radioactive atoms naturally releases neutrinos, and the physicists say that in a coherent quantum state, this decay could or should accelerate, along with the production of neutrinos. This quantum effect should produce an amplified beam of neutrinos, broadly similar to how photons are amplified to produce conventional laser light.
Quote, in our concept for a neutrino laser, the neutrinos would be emitted by a much faster rate than they normally would, sort of like a laser emits photons very fast, says study co-author Ben Jones, a PhD from 2015. And that's when he got it. I wonder why they put that in the article. An associate professor of physics at the University of Texas at Arlington.
As an example, the team calculated that such a neutrino laser could be realized by trapping 1 million atoms of rubidium-83. Normally, the radioactive atoms have a half-life of about 82 days, meaning that half the atoms decay, shedding an equivalent number of neutrinos every 82 days. The physicists show that by cooling rubidium-83 to a coherent quantum state, the atoms should undergo radioactivity decay in mere minutes.
The team hopes to build a small tabletop demonstration to test their idea. If it works, they envision a neutrino laser could be used as a new form of communication by which the particles could be sent directly through the Earth to underground stations and habitats. Maybe submarines could use that too. The neutrino laser could also be an efficient source of radioisotopes, which, along with neutrinos, are byproducts of radioactive decay. Such radioisotopes could be used to enhance medical imaging and cancer diagnostics.
For every atom in the universe, there are about 1 billion neutrinos.
That's crazy.
That is crazy.
For every atom.
Because atoms are not very big, right? They're pretty
right, and they're abundant.
Right. A large fraction of these invisible particles may have formed in the first movements or moments following the Big Bang, and they persist in what physicists call the cosmic neutrino background.
Ooh.
Neutrinos are also produced whenever atomic nuclei fuse together or break apart, such as in the fusion reactions in the sun's core and in the normal decay of radioactive materials.
Several years ago, Formaggio and Jones separately considered a novel possibility. What if a natural process of neutrino production could be enhanced through quantum coherence? Initial explorations revealed fundamental roadblocks in realizing this. Years later, while discussing the properties of ultra-cold tritium, an unstable isotope of hydrogen that undergoes radioactive decay, they asked, could the production of neutrinos be enhanced if radioactive atoms such as tritium could be made so cold that they could be brought into a quantum state known as Bose-Einstein condensate. Why didn't I think of that? Right?
Right. A Bose-Einstein condensate, or BEC, is a state of matter that forms when a gas of certain particles is cooled down to near absolute zero. I'm not quite understand. Absolute zero, I mean, that's just zero, right?
Yeah.
Okay. At this point, the particles are brought down to their lowest energy level and stop moving as individuals. In this deep freeze, the particles can start to feel each other's quantum effects and can act as one coherent entity, a unique phase that can result in exotic physics.
So just to give you an example, Han Solo, when he was frozen, absolute zero.
Oh, yeah, and then and he came back, right?
Right. So it's possible.
I only
come
thought
back.
you could do that with like reptiles. You know, you can freeze a lizard and it'll come back to life. Or
Bose-Einstein.
Okay.
BECs have been realized in a number of atomic species. One of the first instances was with sodium atoms. That's freaky. By MIT's Wolfgang Ketterl, who shared the 2001 Nobel Prize in Physics for the result. However, no one has made a BEC from radioactive atoms. To do so would be exceptionally challenging, as most radioisotopes have short half-lives and would decay entirely before they could be sufficiently cooled to form a BEC.
Nevertheless, Formaggio wondered if radioactive atoms could be made into a BEC, would this enhance the production of neutrinos in some way? In trying to work out the quantum mechanical calculations, he found initially that no such effect was likely.
Several years later, that's what happens in science. Several years later, so he put a pin in it, Jones revisited the idea with an added ingredient, superradiance, a phenomenon of quantum optics that occurs when a collection of light-emitting atoms is stimulated to behave in sync. It's kind of like a burst of light, the strobes, I don't know. In sync. In this coherent phase, it's predicted that the atoms should emit a burst of photons that is super radiant or more radiant than when the atoms are normally out of sync.
So is a photon a picture of a neutron or a... No?
They're different.
They are.
Yeah.
Okay. Jones proposed to Formaggio that perhaps a similar superradiant effect is possible in a radioactive Bose-Einstein condensate, which could then result in a similar burst of neutrinos. The physicists went to the drawing board to work a literal drawing board.
We've got the equations.
We got pins, we got a pegboard, and we got a drawing board. Okay. Went to the drawing board to work out the equations of quantum mechanics governing how light-emitting atoms morph from a coherent starting state into a superradiant state. They used the same equations to work out what radioactive atoms in a coherent BEC state would do.
See, this is where the actual computation...
It's finally getting over your head?
It's finally getting over my head, because I can't fathom taking calculations and then turning it into real neutrinos. You know what I'm saying? I can't. That's a jump that I can't.
Welcome to my world, Steve.
To test their concept in theory, the team calculated how neutrinos would be produced from a cloud of 1 million supercooled rubidium-83 atoms. They found that in the coherent BEC state, the atoms radioactively decayed at an accelerating rate, releasing a laser-like beam of neutrinos within minutes. Fascinating.
Now that the physicists have shown in theory that a neutrino laser is possible, they plan to test the idea with a small tabletop setup. Maybe they could come and do it on your tabletop.
Maybe the backyard tabletop.
The pair acknowledged that such an experiment will require a number of precautions and careful manipulation.
Blowing up.
Right. Quote, if it turns out that we can show it in the lab, then people can think about it. Can we use this as a neutrino detector or a new form of communication, Formaggio says. That's when the fun really starts.
Physics is fun.
I'm ready.
See?
I'm ready. Yep.
You thought it was pain, torture, and agony.
Yep. Yep. I know. I love physics class. Mr. Smith, man, he was a good teacher. I liked him a lot.
All right, folks. Thanks for joining us. Come back to us in the morning, and we'll have more content for you.
Take care, everyone. Have a good night.